Good afternoon everybody, and welcome to the first video in a series of worked exam answers. Those of you who have followed me on TikTok or Instagram will have seen that I've posted things like this before on those accounts, but I'm hoping to add to that on my YouTube channel by covering lots of different exam questions, different style of questions, different level of questions from all different specifications. And today we are starting with an AQA AS back titration question. For those of you that haven't been following me on TikTok or Instagram, there is a backlog of videos that you will find there. But what I like to do is go through the question and highlight the key information that we're going to need. Now, because this is a titration, I've got my red and my purple pens out. I always do red for the acid and purple for the alkali. I always have, I always will, but I would highly recommend two colours, if not red and purple. So I'll highlight the information and then I'll work through the steps of the calculation and explain everything as I go along. So in this question we've got an unknown diprotic acid H2A, and we can see that we're reacting that acid with sodium hydroxide and they are reacting in a 1:2 ratio. That'll be important in a moment. We're making up 250 centimetres cubed of the H2A solution by dissolving 1,300 milligrams of H2A in water. That's then going to go in the burette, and I know that that's going into the burette because we are adding the sodium hydroxide into the conical flask, and we're adding 25 centimetres cubed of that with a concentration of 0.112 mole per decimetre cubed. They've then given us the results from the titrations, our final start and titer values from the burette, and I've highlighted these two here because these are the concordant ones which are within 0.1. And our goal is to calculate the MR of H2A. So I've made this little table here, which I'm going to fill in a second with information from the question. We're going to be able to calculate the moles of sodium hydroxide. Using the equation, we're then going to be able to get the moles of H2A in whatever this mean titer is. We then need to get the moles in the original 250 centimetres cubed solution and then use the mass in grams to get the MR. Let's have a go. So I converted the volume of sodium hydroxide from centimetres to decimetres cubed, and I copied down the concentration, and I used the volume and the concentration to get the moles of sodium hydroxide. Because the acid and the sodium hydroxide react in a 1:2 ratio, I then divided that number of moles by 2, and that told me the number of moles in this volume, which is the mean titer calculated there. So I first of all converted the 25 centimetres cubed of sodium hydroxide into decimetres cubed by dividing by 1,000, and then I copied down the concentration that was provided in the question. I used those two numbers to get the moles of sodium hydroxide as 2.80 times 10 to the minus 3. Now, because the H2A acid and the sodium hydroxide react in a 1:2 ratio, which we get from our balanced chemical equation, I've then divided the moles of sodium hydroxide by 2 to get the 1.4 times 10 to the minus 3 moles. That is how many moles is in this volume here, and the 26.45 comes from the average of the two concordant results. So that is my mean titer. Add up the two concordant results, divide it by 2, gives me 26.45 centimetres cubed. Now, we were told in the question that they'd made up 250 centimetres cubed of the H2A, so the next step is scaling up. Well, if I have this many moles of H2A in that volume, how many moles do I have in 250 centimetres cubed? So I worked out what the scale factor was, which was 9.452, and I multiplied how many moles we had in the smaller volume by the 9.452 to get how many moles of H2A we would have in the 250 centimetres cubed. Now we've got the moles, we can use mass and moles to get MR. So the mass we were given in the question was given in milligrams, so I've divided that by 1,000 to get it into grams, and then I've done that mass in grams of 1.3 divided by the moles of 0.0132, and that gives me an MR for H2A to 1 decimal place of 98.2. Hopefully that's been helpful. Obviously, if anyone's got any questions, please feel free to hit me up in the comments and I'll be more than happy to explain. Hope you have a lovely rest of your Thursday. Thank you very much for watching.